Di cosa l'hai detto? Chiaro. Non ci può, no. Questo guarda. Ora. Questo io non riesci a fare uso sulla velocità. Vuole c'è scaffo per dare una cosa va bene quello vai anche la spedizione di uso il banale si carica una conoscenza le sue riguardanti non so facile per loro ma ti stai vedendo quindi io per casa cosa che conosce ma che no cosa che noi la casa buona macchina vedi po', ma se vedi po', c'ho questa catena tutta tua, sai. Guarda, se mi sono anche dato dei cursi, non c'è proprio. Salve, mi va una maniera questa. Io ci... Fai manco, eh? So, mi amici. No, no. Buono. Rotation? Rotation böyle yok yani. Ne düşünüyorsun şu rotation? Otherwise, aynı runs. Güzel. Onlar. Babasın var. Çargama olsun. Orada işte. O zaman bir dönem orada bir böyle fazla şey var. Ha? Bir şey mi? Aynen. Beh, non ti sei stato? In realtà, ci ma le cene arrivavano, così piace. Già, come stiamo? Stiamo a מה הייתה כבר עבודה? לא תכננת לעבור? לא כל כך מלא בביורוקרטיה, אבל בעיניי המעוף שם הרבה יותר נשמע חלק. לא יודע. דברים אתה מבין אותך.
עכשיו לרדת, זה באסה.
שאלה מה אתה מגיד?
אין כל סמים.
למה לקרוא את זה לתשות? מה יש שם?
טוב. ובצורה...
לא יודע, השאלה אם היא כבר מעובדת בתוך עשר.
זה לא נקרא סגורי בדיוק. בכל פנים.
אין, יש את זה.
נאמר לי שאני כאילו נמצאת בעבודה. זה היה נאמר לי.
אני לא בוחר שם.
Okay, good afternoon. Let's start. Our topic today is deep learning, and I'm going to explain image analysis. And the reason I'm connecting those two topics together is that deep learning is great for image analysis, and I will try to explain to you also why. So I'm going to start by explaining deep learning. Ask me to fix it, but right. I'm going to start by explaining deep learning and artificial neural network, which is another algorithm for classification, continuing last week class. Then I'm going to give you the basics of machine vision. Very briefly, just a general idea. And I'll get back at the end to the question why ANN or deep learning is good for machine vision. So let's start. So as I told you, these slides will appear again and again. Reminders, machine learning supervised is that I'm giving object images, which we're going to discuss today, with labels. I'm using one of the classification algorithm to build a model. We spoke about it last week. Then I'm going to challenge the machine with another object without label and will ask to get the correct label. Of course, unsupervised meaning that there is no step of labeling. I'm just giving the object, and one of the methods, which is called clustering, will divide them for groups, and this is going to appear later in the course. I'm going to get back to this. So classification, again, a quick reminder for last week. The idea or the task is to identify to which group a new object belongs. Groups are predefined by sets of labeled samples. Those are examples. This is also called training data set, and basically are defined based on particular set of object features. We need to define what are the features that will describe each of the objects. And if you remind, I showed you this slide last week, then that for each object, I'm giving the label, and I should give the different feature that describe the object. I need to collect plenty of them, meaning hundreds of thousands, at least, if I would like to do a good job. Then I'm going to use part of it for training, part of it and build a model, and part of it for testing. And I discussed this in length last week, so I'm not going to repeat it. Then I'm going to evaluate the results, and sometimes I will have to do it again. Model evaluation will come next. I'm going to speak about it later in this course. I don't remember next week or the week after it, but it's going to come soon. Next, after I'm happy with the results of the testing, I can use the model, and then I'm going to give it again object described by the same set of features that I use for training, of course, without labels, and I'm going to get the results, which are basically the labels that I wish. The working assumption from last week, that this is why we can use classification, is that everything can be represented by mathematical function, and this is based on coming from a topic called numerical analysis for math, which is approximation of function that I don't know. I don't have idea how to represent them. And I gave you last week this example that I have one feature and a label. I have examples, and I need examples mean that I know that at this point, let's say this is 20, I know to tell you what is the label. But if I'm going to be asked about this point, or this, I need to first build a model, and then I will be able to try to answer. Whether the answer is correct or not, I don't know. This is the whole idea of trying to measure the how well this model is doing, which I'm going to describe later on. Till now, everything was last week. Just a quick reminder. Questions before I continue? Okay. So, what are ANN? ANN are artificial neural networks. Those are creatures that their components are circles and lines, as you can see now. Now, the circles represent neurons. This is why it's called artificial neural network. Okay, this is a network of neurons. So first, what is a neuron? This is the biological neuron. Neuron receives, each one of us should have at least many of these in his brain. Neurons receive signals via their dendrites. What are dendrites? Those, okay, those are called dendrites, and do something about it and send out signals down the axon. This is the axon. And the axon is connected to many other neurons by, again, dendrites. Okay? So this is basically the way our gray stuff works. And each neuron do something very minor. It computes something. This is actually what is happening. Of course, in our brain, it's about chemics and about electricity, which I'm not going to get into it. But the whole idea is to try to mimic this concept by numbers. Okay, this is the idea. So ANN is based on a collection of connected nodes. Each node is trying to mimic a neuron. It's an artificial neuron, and it computes some function. Those functions usually are very simple function, like a linear function. If you recall, linear function is take the number, multiply it by something, and add something, like a multiplied by x plus b. This is a linear function. There are other functions that can be computed in this neuron, but all of them are very simple ones. I'm not going to get, as I promised, into the mathematical details. Nodes are aggregated into layers. back to the picture. So we have now neurons. Each neuron computes, each of the circuits compute some function. Usually all of them compute the same one. This is the concept, but not necessarily. We'll see later on. And we are arranging them in layers. There is the input layer, there is the output layer, and there is inside something which is called the hidden or internal layer. Okay? Till now, questions? Edges, the links, can transmit a signal. Like in our brain, there is a signal coming out of the neuron, and these are numbers, simply numbers. Nodes and edges have a weight that adjusts as a learning process. Back to the picture. So we have neuron, each one of the neuron can compute a function. The result of the function is a number that is going to be sent out to the next neurons, as you can see. And we have another number that we just multiply. So if we are going to say here, 1, for instance, and for this, the n stands for a number, let's say it's 5. So we are going to multiply 5 by 1, and we are going to send it out. Okay? So we have here a number that are sent out from each of the nodes, and we have flexibility by weighting the numbers by multiplying by these parameters, which of course each line has this number. So everything here is just playing with numbers, nothing more clever than this. There are many, many numbers here moving around the network, multiplying, maybe have some kind of computing here, and then multiplying again, just playing with numbers. Yes.
It's different number in each.
Yes, yes.
Is there only one hidden layer or many hidden layers?
No, currently we are speaking about artificial neural network. There is only one. Wait a few slides and we'll see it expanded. Okay?
And then the number from one node is being sent to all other nodes?
Yes. Yes.
But this is like excessive, it's no?
No, but this is the model. You can say it's not a good model, maybe, but this is the model. Now in our brain,
Does it mean that it brings more load on other nodes instead of actually optimizing the process? No? Or I get it wrong?
no. We would like, we wish to make it like this, and you will see later on why. But currently, the idea is that each number that is computed here is going to be sent to all other neurons in the next layer. Okay? Now, in our brain, this is trying to mimic what is going on in our brain. Now, this is not the way it is arranged in our brain. We have plenty of neurons, many of them, millions or hundreds of millions of them, and they are combined in many, many ways. They are not combined in layers. It's a mesh. It's a very complicated network. This is the way we try to mimic it on computers. Okay? More questions?
And the purpose is like to calculate faster.
Why to do it in layers?
Why
It's more convenient for computers. We can also arrange it in a full mesh connecting everything to everything, but it's going to be a mess and it's harder to manage.
The function is happening inside the node or on away from one node to another?
Inside each node, there is a function.
Only inside.
And also, I said, whenever there is an output for one node, it is going to be multiplied by the number that is written on the way, on the link. Okay? So there is multiplication here and computation there.
So the operation is also happening on the go,
On the what?
on the way to one node to another node.
Yes, yes.
The
Let's say
operation-
this computes something and the result of the computation is 1. Okay, so here I have a weight 5, so I'm going to send 1 multiplied by 5, it's going to be 5. Let's say here it's written 4, so I'm going to send 1 multiplied by 4, so here I'm going to send 4. Okay?
So it's not just the link between two nodes.
It has a
also
weight.
Operation.
Not operation, just weight limit.
Huh?
Nothing more than weight in it. Okay, just let's say it's 1. I can send it as a simple 1, or make it larger by multiplying it by 5, or make it smaller by multiplying it by half. Okay, the signal is 1. I can just adjust, let's say, the volume.
And the mathematical operation that can happen there, it's also only simple operation. Or there should be like
Here?
no, from one node to another.
Multiplication only, just multiplying the numbers. There is a result of this computation, and I'm going to multiply it by the numbers written on the links. That's it. Okay? More questions? Signals in this model travel from the first layer, which is the input layer, to the last layer, which is the output layer. Again, back to the picture. It means that I'm going to put input here, and everything, all computation is going to be conducted only in this direction. Okay? It's directed. So let's say now I put here the inputs, the images, and I'm going to explain later on how actually a computer represents those images, again, with numbers. So numbers are going to be entered here. All this computation is going to happen, and at the end, I'm expecting to get the labels, either Apple or not Apple. I'm not going to get labels. I'm going to get numbers, which I'm going to translate to labels. Everything here is numbers, nothing else.
The numbers are representations of.
Yes, yes. And we are going to discuss today how can we represent images with numbers. Yes. So how this can learn? The idea of learning in this model is by adjusting the weights, the numbers on the edges. Okay? And while we adjust those numbers, we can improve the result accuracy. And we are trying to minimize the error, meaning the deviation from the truth. If you recall, what is error? I explained it last week when you spoke about regression. I can measure the deviation between the truth and the model. This is error. And I strive to minimize this. Okay? So I can compute in this network, and my idea is to try to minimize the error. So as long as the cost function, meaning the error function, continues to decline, meaning I'm getting better, I have less error. If you recall, last time I showed you a website of a regression, and you saw that the line moved, and we get less and less errors. So this is my goal. And I'm using some kind of optimization and statistical estimation method how to do this conclusion of calculation of error, which I'm not going to speak about. And there is a method which is called backpropagation, again, another algorithm, which I'm not going to speak about, to adjust the weight. And the way it works, again, schematically, is like that. There is some kind of, as I said, input here. Computation is done only in this way. Now, at the end, I get result, right? I put some input and I see the result. It could be error and it could be right. Could be right or wrong. So I have here a cost function, meaning I'm calculating the error, and I'm going to send, of course, not only one example. I'm going to send many of them. Okay? So I can wait for each of them. What is my error? I can calculate this. Based on the calculation of the error, I'm going to do what is called backpropagation. I'm going to go back to the network, and layer by layer, I'm going to change the weighting. And then I'm going to repeat this, and I get another error, and I'm going to get back and change the numbers. Repeat, change the number. Repeat, change the numbers. How many times? Plenty.
And this training, that's called.
This is the training. Yes. Now, as last week, there are good people who are producing websites that help lectures to see this. And this is called TensorFlow. It's one of the most famous packages to do AI nowadays. And it's a demo site of their packages. Of course, if you know to program, then you can do more than this, but I'm not teaching you how to program. I got just this is an example. So what we are going to see here, we have two features, X1 and X2. And again, feature 1, feature 2. And these are my examples. And we'll see when I'm going to run it that we are trying to classify the space between oranges and blues. Okay, now they are using here two colors in this presentation, orange and blue. Unfortunately, they are using the same colors for two different meanings. I don't know why, but this is there. If on the links the number is positive or negative, they'll use the colors, and also here they use it to represent the results. It's confusing, but unfortunately, this is the way they pick to do it. And as before, if you will recall last week, we see here the epoch. Epoch is how many times we run it. Okay, so let's start. I'm just going to do step by step first. So you see here, there the error. The error is very, very high, of course, because we just started, and you don't really see anything happen. Let's continue. Still, if you can see the orange and bluish doesn't look quite nice. And what we have here, as you see the weights, the numbers, okay? Here is 0.21, here is minus 0.31. If it's negative, it's orange. If it's positive, it's blue. Why? I don't know. Let's let it run not only 10 steps. Okay, it's look better. And we got the result. Okay, so now it means I can stop it by now. So I get mouse. So we have about 500 runs of back and forth. Okay, those numbers will change. How can I tell? Because it's now weighted. You see, they represent the amount of the size by this. So if you recall, it was 0 point something. So now it's minus 1 point something. Okay, so they adjusted the number, and we see here good classification. So those are the orange examples, and basically everything here will be classified as orange. Here we have the bluest example, and everything in this region is going to be classified as blue. Okay, this is the idea.
Now, from the neurons to the output, it's just the result, right? The line.
Yes, this is the output. So we have here, this is the input layer. We have only two. We have here the hidden layers with 3 neurons, and we have the output layers which they are representing as the results. Okay.
And so nothing happens, no manipulation.
In between? No. What you see is what you get. Okay? That's the idea. Now, if you try to understand why we are doing this, because don't try to. Just playing with numbers. It's not that I cannot explain to you. This is the truth. It's just playing with numbers. That's it. Okay? Okay, back to the presentation. So, what is the pros and cons for this method? Pros, once trained, this method, its prediction are pretty fast. It's very fast to do one go on this net. The training takes a lot of time, but just to calculate those numbers, it's just very simple function. It's very fast. It can model data with very large number of inputs, like images, which I'm going to explain later on. Images has thousands or hundreds of thousands of input numbers. The cons.
Number of inputs, you mean
large number of samples
No,
or samples with large
no, 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 no,
number
no,
of,
no, 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 input numbers, dimensions,
okay,
okay?
so,
Not number of samples.
okay, because each sample can have a lot of dimension and
Yes, yes,
numbers and.
like images. Images has plenty of dimensions. Cons are black, it's a black box. You can't tell how it works or why it works. Again, it's not that I don't know how to explain to you or don't want to try to explain to you. This is the reality. It's just playing with numbers. It's a black box. We just put something in the beginning, we do something, and we get the result at the end. And why? Because
But we see clearly how we do it. We see the function, what's happening, we know the weight,
yes,
With the
yes,
seal?
yes, but of course, in useful networks, there are not two neurons, there are much more. So you can look at the numbers if you would like, but why this is 5 and not 4.7, I don't know. Okay,
No one.
no one knows. No, we just playing with numbers. Now it requires a lot of training for real world problem. This is what you asked before. You require in this to train this kind of networks, you're going to be required to supply hundreds of thousands of samples to begin with. And of course, as I explained last week, there is the issue of overfitting. I'm going to explain or remind you again. Overfitting is that I'm trying to build a model which fits too well to my example. If you recall last week, I said I'm just going to use new lines to try to model those examples. It looks perfect, but if I know that now I collected more samples, this model is better than that model. So if I'm trying to be too specific on the examples, it's not good. I'm going to be, when I'm going to use the model, I'm going to be wrong on many examples. This is why I need to keep some generality. I cannot fit too well the samples. This is overfitting. Okay, so this is the whole story of what are neural networks, of course, without the many mathematical details. And the history is that they were first suggested in the 50s of last century. It's not a new concept. At the time, there were no computer power to develop it. So basically, practical ANNs start to appear at the 80s, only on the 80s, okay? Then it was a huge buzzword at the early 90s. Expectations were in the sky. Well, we are now mimicking the way the human brain works. So soon enough, we'll have artificial intelligence that can do everything. Why? Because we are mimicking the human brain. Well, no. Mid-90s, huge disappointment. What do I mean by huge disappointment? I mean that at the time, I was working with ANN at the end of 80s, and at the 90s, when I met people, when people tried to explain to me what they are doing, they started by saying, well, we are doing AI. We are not doing neural networks like all those fool guys. We are doing some other methods. What are the other methods? SVM, which I explained to you last week. If you recall, SVM was dividing the plane, try to divide between the groups. This was the prom queen at the 90s. If you didn't hear about SVM nowadays, there is a reason, because it's not such a good method. Okay, but everything works like this. And I think I mentioned it in the first class. This is Gartner Hype Cycle. Gartner invented it, so let's give him the credit, but this is the reality. There is a technology trigger. Somebody is come up with some idea, technological idea, okay? Nobody actually hear about it besides his circle of academia or company, etc. Nobody know about it. Then the press hear about it. And we get big on inflated expectations. Many people that know how to speak, but have very, very little brains, start to speak about it. and it's going to conquer the world, and it's going to do everything, etc., etc., etc. And then there is the throw of disillusionment, because it doesn't. But there is the slope of enlightenment, where it cannot do everything, but it can do something. And there is the plateau of productivity. Now, I've been around and I saw so many technologies, all of them, each one of them follow exactly this path. Nowadays, with deep learning, we are here. Okay?
So why didn't this method met the expectation?
Why? Questions?
The idea with the neural network is to create one network that can fit to all.
No, 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 for each problem.
Okay, so for each problem, you need to develop a network to put the rules,
No rules, no rules. Numbers. There are no
Put the-
rules.
to put the numbers, to set the right
To
number.
train it, and it's going to solve you this specific solution that it was trained for. That's it.
Okay, so you lose the ability to control it once you start to train it. But until you start to train it, you know what you're doing there, and you control the parameters and what.
No, I can train it again. I can retrain. It's okay. But once I finish to train it, I'm starting to use it. That this is what I have. Okay.
Yes.
Yes.
What's this trend theory called?
What is what?
Trend.
The house.
Gartner hype cycle. Hype. Okay. By the way, they Gartner publish every year now. They started with only one of them, a technology hype cycle, one document, and since people were happy about it, and they sold it for about 2,000K a piece, so I sell one. You can find about 50 or even more hype cycles for each vertical in the market. Okay. So if you are interested in some market, you can buy this from Gartner, and you will see they are spreading their technology of this vertical where they expect it on this slope, if you are interested in this. Of course, they are not right on everything. Depends on those who write it. Some of them understand what they are writing about. Some of them are not. So with a grain of salt. More questions? So we ended with a disappointment. But now there is the comeback. Deep learning. Deep learning is huge, huge nowadays. And what are deep learning? The same thing, exactly the same thing. But, and there was a question before, how many hidden layers do we have? More than one. That's it. So if you have a shallow network, you have only one hidden network. If you have a deep network, you have 3 and above. Nobody is doing 2. I don't know why. But usually people are doing between 3 to 6. So this is deep. 1, it's shallow. But the concept that I explained to you, it's exactly the same thing. So back to the website. As you can see, it's the same website. Looks the same, but now it's deep learning. Why? Because we have 1, 2, 3 layers. Okay?
Let's say on each layer, there's a number of.
Here we have 8 neurons, 8 neurons, and 5 neurons. This is the example. And now, if you can see, it's more difficult. If you recall before, they were arranged in the circle and around. This is more problematic. It's more challenging to try to figure out how to model this. So let's let it run. It will take a while. You can see it's getting better and better.
The X1 and X2 in this example, it's a samples from the so
Those dots are the sample set.
so it's one dot by dot by dot by dot as X1 and X2.
No. Yes. Each dot, X1, X2 are the dots. Yes. It's the X and X1, X2 coordinate of the dots.
Yes.
Yes. Well, it's getting better, right? After about 300. And there's still way to go. You can see here, this is the arrow curve. As you can see, it's getting down. Now it's in plateau. So we are not going to do better than this. That's it. Okay? Again, do you want to run it again? Okay. You can, as I said, it's in the slides. I'm going to publish the slides, so you will be able to play with it as you wish. Let's go back to the slides. So, first question, is deeper better? In principle, there is no theoretical difference between a single hidden layer network, as I said, a shallow network, and networks with several hidden layers, deep networks. In practice, it seems that deep networks give better results, and I will try to explain to you why. Okay?
What's happening between the layer in the hidden layer? So a number goes from.
Yes, the same thing.
There is
Exact same thing.
multiplying
Multiply on the line and
Okay.
get back. Yeah, the exact same thing, but
in
instead of
few
three,
stages.
several. Yes. The same thing. So, if we go back to this slide, if you recall, I can build a model. How can I improve it? If somehow I find more examples, then I can try to improve it. And now maybe I'm explaining this region better than I did before. Okay, so this is one way to go. But there is another way to go. Let's say I need now to build a model to represent this curve. Okay? If I'm given, somebody gave to me only 2 lines, the best I can do probably is this. Okay? I cannot do, and I cannot try to mimic with straight lines a curve. This is the best I can do. Okay? If I will be given 4 lines, probably I can do better. Okay? You see now the error between my model in red and the curve in blue. I have less error than before. Questions about this? If somebody will give me now 100 lines, probably I can do even better, but I'm too lazy to draw it. Do you see where I'm heading? Mm-hmm. Now, in order to represent a line in mathematics, you need 2 numbers. One of them is the slope, and the second one is where this number crosses the y-axis. If you recall, y equal mx plus b. 2 numbers, m and b. I need only 2 numbers to represent each line. So here I need 2 and 2, 4 numbers. This is the best I can do. If I have 8 numbers, I can do much, much better. I have more parameters to tune. If I'm going to get 100 lines, I have 200 parameters. So I have more numbers to tune. I can do better. Okay? So back to those networks. What are those networks? Numbers multiplied by numbers. And I told you that there are numbers on the lines, and I can tune them. So if I have more and more numbers to tune, I can do better and better. In the cost, of course, that I now have to tune those numbers. It will take me longer. Do you see? Questions?
I lost you.
Okay. Explain why with 4 lines I can do better with 2. Yes. And with 100, do you believe me that I can do even better?
But when you said the number, it means what, the number of nodes?
Yes.
It's translated.
If I have more nodes, I have more lines, right? On each line, I have a number. It's more parameters to tune.
More nodes, more lines.
more lines, more numbers to play with. If I
And
can,
then the output is also,
no, not the, just the, in the middle. Let's go back. Here, I have number of each line. If I have only 3 layers, I have numbers on only here and there, right? Now I have numbers here, there. I have plenty of numbers to tune. Since I have so many numbers to play with, I will adjust it and I going to do better. That's the whole idea. Nothing more clever than this. Okay, there is a say of Archimedes that if you give me a long enough, I forgot the word in English, manof.
when?
No, lever, I believe. If I get long enough lever, I can lift the wall. Okay, so here, if I get enough numbers, I can model everything. That's the idea. When I get more numbers to play with, I will try to get better and better explanation of the model that I need.
Can I ask you about the input layer? When on input layer we send something to the hidden layer, does hidden layer or output layer return something to the input?
No,
or-
only one way, and the adjustment is doing it the other way. For now, we'll see later on differences.
Adjustment is not through the same nodes.
The way inputs, I'm
Can you
doing the
compare to
calculation in this way, and the adjustment I'm doing in that way. But it goes like this, like that. No mixing in the middle.
But through the same nodes. It's not that some nodes are for the one way and some for.
No, it's the same. The whole network act the same way. Okay. Let's see another example again from this website. You can play with more parameters in this way. You can also play which data set we would like to see. Okay, so here we have 3 hidden layers. Let's reduce the number of neurons. If you recall, for this type of data, I don't really need many of them, and I can do very, very well. Let's run it. As you can see, take a lot of time. Not enough even now. Just a moment. Let's stop it.
Not enough neurons on a hidden layer.
Let's get rid of several hidden layers. Let's start with out there. Let's try it again. Okay, it works. That's all I need. Now let's try to do the same thing, and it didn't took too long. Let's now try to do the same thing, but now let's do the spiral. Okay, let's try to do the spiral with only one layer. It's not going to work. You can wait. Why? Because the complexity of trying to mimic this spiral behavior, I need many numbers in order to try to mimic it. So the numbers that I can use now are not enough. So it's not going to work. We can wait and wait and wait. You see, we're already 600. Is that not look good?
Check the adjustment on the set between trial and error or
Trial and
changing
error.
the weights.
Yes.
That's it.
It's not exactly trial and error because there is a method to minimize it. It's not random. Okay?
But we don't really know how it's affecting.
No.
Like,
We
we're
try,
trying to
there
find-
are algorithms to make it better and better and to minimize it. Okay, it's not random. As you can see here, it's get minimal. Okay, but here it's stuck. You see, we can run it now forever. It's not going to work. So let's try to add the layers. Let's stop it. And let's try to add now 2 layers, make it more deep, and let's add here, let's say, more neurons. Let's have here 8 neurons. Let's have here 5 neurons. I also need to adjust this in order to make it work, believe me.
Number of samples.
I think this is enough. I tried it, I played with it. I think this is going to work. Let's see. So see how much more neurons I need in order to try to succeed, and let's see if it works. If you don't believe, just play with it.
More neuron and more samples, correct? What you did?
No, I didn't add samples for now. The size of the sample is the same. Let's see if it's work. If not, I will going to add samples.
And so what is the ratio of training to test data? So 50% of the study used for test,
Yes.
for training?
Mm-hmm.
Okay. So we are doing training with 15 examples, 1.5?
Yes.
Okay.
It is better, but let's try to add a number of more samples. I don't recall this. How this is done, I don't remember. There is a way. No, I need to add to downside it actually. Just a moment, right. Let's once again. Now, the way it arranged the examples is randomly for each time I run it, so I cannot guarantee that it's going to work, but I assume it is. Okay, it's much better than before. We already see the spiral, and here, since there are no orange examples in this region, it's quite reasonable to declare this blue. And also here. And also here, there is a gap between the orange, so maybe this is blue. Okay? So we needed so many neurons in order to try to make it work. And if you would like, you can play with it just to reduce the number of neurons. Try again and again and again. You see, there is a limit to what you can do with too little number of neurons. That's the whole idea. So if I have more and more neurons, I can try and represent more and more sophisticated words. Questions? Yes.
Increasing the features, really.
Increasing the what?
Features. The inputs, number of features.
Oh, here?
Yeah.
Yes, I can play with this, but then I need to explain why are those different features. I'm not going to do it. But go ahead, you can do it. There are plenty of here. If you can see here in the URL, there are many, many parameters you can tune. I just, at each of the stages, I just tuned it to a specific purpose. So, but you can play with it a lot. More questions? Yes.
First layer and last layers.
What else, right?
Why aren't there connections between the first and the last layer? Isn't that
Oh, because it works in layers. The input from here goes to the next layer, and from here, this layer to the next layer. This is the platform. This is this is the way that we are arranging it. You can think about connecting everything to everything, but it's going to be much more complicated. So we are arranging it in layers, and the whole idea is that this layer can see only input from that layer. That's it. It's simpler for the computer to handle it.
isn't it faster if you generate bypass?
Not necessarily, because again, I input here numbers, do some kind of calculation, and get there an input. Since this is a black box and we don't really know what is going on inside, maybe it's going to be better, maybe it's not. We don't really know. Okay, so the architecture tell us, make it simple. And simple is just to connect each layer to the previous one, and that's it. Okay, now you can try to do other architecture. It's okay, people are trying to do it, but then things are much, much more complicated, and happens to be, it's much more complicated to tune. Okay, because of the simple architecture, it's easier to build an algorithm how to play with these numbers and tune them. If you have everything connected, then the tuning work is going to be a mess. Okay?
How are nodes being interconnected? They're interconnected physically or through the wire? How do they send those requests to another one?
Oh, those are just numbers. In computer, everything is represented by numbers.
Yeah, but how did it being sent? So through the language, through requests, how is it being sent? How is it being transmitted?
You mean about the implementation? It depends.
Between nodes.
It depends. Nowadays, there are companies that are doing it in hardware. If you heard about NVIDIA, for instance, okay? So they are doing it in hardware. You can do it also in software. There are many ways to implement it, which I'm not going to get into. Okay? Now, as you can imagine, we are going to speak about images soon. There are plenty of inputs for images. This is why you need hardware. This is why you need very, very fast hardware. Okay, let's go back to the slides, and we are going to do a break soon. So the pros and cons of deep learning are exactly the same ones as for NN, because it's exactly the same thing. However, I emphasize that for deep learning, it requires a lot of training. In real-world problem, it is going to take a lot of time. And when I speak about a lot of time, I'm speaking sometimes on days or even weeks, not minutes, okay? Because since you have so many numbers to play with, it is going to take a lot of time to play with them in order to get to a specific results. And by the way, nobody guaranteed that it's going to work. We're going to discuss this later in the course. So, why is deep learning successful nowadays, where ANN, the shallow networks, fail? Because of cyber. First, computing power. At the 80s or 90s, when I used neural networks, I have very, very, very slow computers. Didn't I know that it's better maybe to try more neurons or to try deep learning? Of course I knew. Everybody knew. But we cannot do it. We cannot afford it. Okay, because we didn't have so much computing power as we have today. And the reason we have so much more computing power today than before is cyber, because you can see that it's quite aligned with cyber. When cyber and web was started, the demand for power, computing power, raised dramatically. And for this, the price went down. Okay? Next, data. If I would like to build a classification network in the 90s to classify between dogs and cats, I need examples of pictures of dogs and cats, right? In the 90s and 80s, how can I find them? In books, maybe. There was no web. I can took my own camera, go on the streets, looks for dogs and cats to take shots, right? I also remind you and also tell you, those who are younger, it was film, it was not digital. Okay? So I now need to take my photos and digitize them in order to learn. So in the 90s, nobody can do this because there was no data. Nowadays, if you would like to classify dogs and cats, well, some people say that the internet was invented for pictures of cats. Okay? You can have plenty of pictures of whatever you wish because of the internet. And as I told you, for deep learning, you need a lot of examples. Now we have them. In the 90s, we didn't. Simple as that. So computing power, data, and there is a third reason. Modern slaves. Each one of us, when we use whatever service on the web, like Google Translate, for instance, and the translate didn't go well, so we say, okay, let's try it again. This is an input for the learning algorithm. It's a feedback, very priceless, precious, sorry, feedback for the algorithms. So nowadays, we have a lot of computing power, very cheap, and it's getting cheaper and cheaper. We have a lot of data for many, many interesting problems that in the 90s I can only dream of. And we have slaves that help us.
I didn't understand the last one.
The slaves, one of the things in order to make things better in classification, for instance, is that to get feedback, here you were wrong. How can you get it? It's hard task, okay? But nowadays, for instance, Google Translate, whenever you translate something on Google, and it doesn't sound right, you will tell it, translate again. Or let's think about search engine. You search for something and you didn't get the result. So you are going to add more words, right? It's feedback for Google that it went wrong the first time. And they use it to learn. Okay? It's their input, supervised input for the next wave of learning. And it's very, very important for them and for any other company.
And this wasn't available in the 90s?
No, there was not web.
Like you couldn't reach the user.
Yes. Nowadays, if I would like to train something, there is a website, for instance, called Mechanical Turks, that you, for a few cents, you ask people to help you to label. Okay, there are many people in India that make a living like this. How can I find them by the 90s? No way. Okay? So the reason that deep learning is so successful today, not because people are more clever today than for the 90s, but they are computing power, data, and modern slave. Okay, let's stop here. We'll meet again in 50 minutes in 4:25.
I can't. Oh.
Okay, let's continue. Okay, nowadays, deep learning is very successful and is very successful in several fields. And I'm going to explain to you one field why soon. I'm going to speak now about application. What can we do with deep learning or with ANN? Nowadays, facial recognition for many purposes is using this technology, and it was a huge leap forward of the quality of facial recognition. Nowadays, also character recognition is used this technology. The autonomous car must have this technology. We're going to speak about autonomous car later today a bit. Cancer detection or in health, everything that is involved imaging, whatever, is used deep learning. Automatic machine translation nowadays is using deep learning, and I'm going to dedicate the class for text, and I'm going to speak about it. There are some
translation mean the translation is
Google Translate and some satellite image processing. Many more applications nowadays are using deep learning. Deep,
Yeah,
what?
that you can use with
I said
all
stupid.
which translate.
I don't hear it.
I'm asking to translate. It's not a simple stupid dictionary. It's
No.
Context translate.
It was trying to use a dictionary in the past, but nowadays it uses deep learning, and was a huge leap between, I think, in the last 10-15 years between as it was before and the quality of here of nowadays. And I'm going to speak about why when we're going to speak about this. Deep learning is great, actually really great for vision. I'm going to say some words about this slide, but I'm going to repeat it after. I'm going to explain to you how images are represented by computers. The reason that deep learning is great is that all required information for learning for images is pixels, which are a digital presentation of images, which I'm going to explain in a minute, and mathematical function. And those creatures, as I told you, know to handle numbers and mathematical functions. So this is why they are so great. And human brain specialize in image processing, but humans fails to explicitly point out the feature they use. If you recall the dogs, so it means that using neurons can do great by classifying, because it's a black box, we don't need the features. And let's speak a bit about machine vision so you will be able to understand why. What do you see here? Can you tell me if those lines are parallel or not?
Which line? They are parallel?
Yes? Do you see them as parallels?
from our point of view, they are
They aren't.
Yes.
from our point of view.
Yes, but they are. Okay, because of the perspective, they don't look parallel, right? Next, what do we see in this image? Yes, but how many people are we seeing? No, there's one person and one dwarf.
And one what?
Dwarf. I just copied this image, copy paste, okay? I just put it the same here. If you are not convinced yet, this is the box, and let's take out the background. Okay, let's go back.
But it's a perception.
Yes, this is the whole idea of the slide, to explain the meaning of perception.
Hmm.
So the way we as humans see things, we don't really see what is actually there. In our brain, there are a lot of more things that happening. And although we consider now what we see here are two regular men, it's not what is actually going on there, as I told you, okay? Why this is important? Because I'm going to explain in a minute how to represent images in computers. And the way images are represented in computer are totally different from the way that we see. So don't try to understand what is going on. Don't know. Because there's one way to represent images for us and our brain doing a lot of stuff on them. And there's another way to represent images on computers. This was the point of this concept. So this is a picture. And we see here a creature. And let's explain first what is a pixel. Pixel is a word that stands for just combining picture element. And a pixel is this box. Okay? That's it. This is a box that is a pixel. Okay? The way we see this image is as we see it now. The computer can't see, but the computer represents this image with numbers. Surprise, surprise. And the way it goes, there is a matrix. Okay? Each cell is a pixel. Okay? And where we see black, we'll put 0. And white, there is going to be 1. So this represents both what we see and what the computer see. But this is the image as the computer see it, actually. Now we don't see the creature. Okay? So the way human sees and the way computer sees are totally different. Okay? So the way to represent images in a computer is just by numbers. If you go back, wherever there is white, we are going to put 1. Wherever there is black, we are going to put 0. That's it. And we have a picture represented in a computer. Simple as that. Okay? Next, grayscale. We don't want only images in black and white. We would like to have also grayscale. So what are we going to do? Instead of putting 0 and 1, we are going to put other numbers. For instance, here we have a little boy. This is zoom in for this region. Well, and this is zoom in for this region. As you can see, as the color is brighter, then we see larger numbers. So instead of 0 and 1, we have now numbers from 0 to 256. Okay? And as the number is larger, it's more brighter. As it's smaller, it's darker. That's it. Questions? Okay, so it can range from 0 to 255. Why? Because it's a multiplication of, it's a power of 2. Okay, everything in computer comes with the power of 2. Okay. Questions? Next, let's speak about resolution. Resolution is just the matter of how many pixels do I have. If I have high resolution, in this case, 100 pixels by 100 pixels, meaning 10,000 pixels, I can see a very good resolution. If I take down the number of pixels, the resolution is getting worse and worse and worse until, of course, with only 1 pixel, I can actually see the picture. Okay, so this is higher resolution and this is lower resolution. Resolution just means how many pixels by how many pixels do I have. That's it. No complicated than this. Okay? If you speak about TVs, it's the same thing for TV screen or images. If you have high definition, high resolution, more pixels. If you have 4K, means that you have 4,000 pixels in one dimension. That's it. Okay? As you can see, if I'm going to have more pixel, it's the same concept, by the way, that I explained before with the parameters of the neural networks. If I have more numbers to play with, I can represent things better. Okay? The same concept. What about color? Very simple. I told you that I'm going to use a matrix between 0 to some number. If I need colors, all I need to do is have 3 matrices. R, G, B. If you recall from your kindergarten, you can mix colors to get more colors, right? So I need only red, green, and blue in order to get the whole variety of colors in the world. So if I have a grayscale image, I can represent it with only 1 matrix of numbers. If I would like color, I need 3 matrices. But the same things follow. I'm going to put here numbers. Lower numbers darker, higher numbers lighter. This is the whole story of how to represent images in computers. Questions? For instance, I can do something which is called color histogram. Here we have these numbers, and here we count how many of each of them we have. Okay? So if we see here the same picture of Vincent van Gogh, it's called Starry Night, I believe. So if we have a more darker version of the picture, see that the lighter color are missing. So it's become darker. Okay, so just play with the numbers, you get lighter or darker views of the same image. Okay, that's the whole idea. So what I can do with those pictures, and I'm going to speak only about stills image. Yes, almost the same concept follows for videos, but I will focus on stills. I can do what is called first preprocessing for images. For instance, noise reduction. If I have some problems with the image, then there are algorithms to just know to fix it. I can enhance the contrast between the darker and lighter. I can try to take out features like lines, edges. I can find corners. I can find shapes like circles, rectangles, etc., etc. I'm going to speak about some of them in a minute. Also, I can segment the image, for instance, the background and the foreground of the image. I'm going to explain this in a minute. And also, I can try to cut out regions that contain a specific object, like in the image has many objects in there. I can just cut a part of it. All of these are preprocessing that I can do. How can I do all this? Very simply, by using something which is called filtering. What is filtering? Playing with numbers. I have some kind of a small matrix that I'm going to use it to run, as you can see in this representation, all over the image and change it. I'm going to run for a moment because I have later on, I have a way to here. Okay, this is an image that explains this. You see here, this is the small filter. And what actually I'm going to do is that I'm going to move this small filter across the image and do some kind of calculation. What actually I'm doing, I'm going to get back to this to explain later on. Okay, where will we? Very well, here. So what I can do with this little matrix that I'm moving around, if I just represent everything with 0, but only the pixel that I'm working on as 1, then this is called nothing. Okay? If I would like now to blur the image, what can I do? What I'm going to do is use this type of matrix. You see, everything is 1. Okay, and I'm going to multiply each of these numbers by the vicinity of the pixel that I would like to work on, and multiply by 10. So, sorry, divide by 10. Why? Because we have 10, it's actually averaging. Okay? 9, so it's averaging, okay? Meaning I'm taking the number that is written in the pixel that I'm interested in, and I average it with its neighbors. Okay, and then instead of taking this number, I'm going to put back the average, but I'm going to get blurred. Why? Because the neighbors affect this pixel. If I'm going to do the opposite thing, meaning I'm going to ignore those in the corners, I'm going to downsize those that around, and I'm going to elevate my pixel. By multiplying it by 5, I'm going to get sharpening. Okay? Because now I'm going to focus on the image of the pixel. So averaging is blurring. This is sharpening. And if I would like just to what is called extract the texture or the lines that represent it, okay? Then what I'm doing is, look, everything is going to downsize, and I'm going to emphasize the line, so I'm going to get just the contour it's called. So everything that you see in applications that are doing manipulation for images, adding filters, doing several things, it's just taking the picture, which I recall, it's just numbers, and multiply them with this small matrix. That's it. And I'm going to show you later on what this multiplication looks like later on, okay?
And each number is fixed.
Each number is multiplied by a pixel. Okay, let's go to this slide again, and I'm going to explain this. Maybe I should put it here. Okay, I cannot stop it, so I'm going just to put the menu in order to stop this video, okay? So look, this is the small filter, it's called. And now I would like to do something on this pixel. So I'm going to take all its surrounding pixel, and I'm going to do something which I'm going to explain in a minute. And the result of this something I'm going to write in the output. Okay? So what I'm doing, let's continue. First, since it's in the edge, and I would like to do something, I just copied those numbers at the side. Okay? Now, what I'm going to do, I'm going to multiply 0 by 7, minus 1 by 7, 0 by 6, 7 by minus 1, 7 by 5. Okay? Just multiplying number. Anything more sophisticated than this. And then I'm going to add up everything I got, and I got 9. Let's run it. Okay, it go over the multiplication, and I get 9. So now I'm moving, and I'm doing the same thing on the next pixel. That's the whole idea. Told you, playing with numbers. Yes, question.
Yeah, at the first square, it looked like the matrix was existing outside of the picture. How is that possible?
It's not, but I need to multiply this in order to affect this pixel. So what is the trick? I'm just copying as it was there, phantom numbers, so I can do the trick. That's it.
So a matrix will, the whole matrix is multiplying that one pixel, just the 7 at a time.
Its vicinity. You see, I have here 3 by 3, so I have to multiply 3 by 3.
And it's kind of creating the 3 by, like,
I'm creating this. You see, also here I create only those because now I work from this. Okay.
okay.
So I need to extend my image artificially in order to be able to multiply. It's going to run again. That's right. Okay. So in order to be able to multiply this, I just extend my image by adding those fake numbers.
And you could probably have a filter that's not 3 by 3, that's like 100 by 100.
No. Most filters that people are using are either 3 by 3 or 5 by 5. No more than this.
Even for videos, for
Yes.
I have a question. For the input, how do you know which numbers to put in? How do you know to put in the 7 in that corner, 6, 5? And
Oh, I just copied. Look, 6 to 6, 5 to 5. I just extend.
Oh, I understand that.
That's it.
But I'm talking about just for,
Oh, about the filter itself?
no, not just like the input. So you see how,
This is the input image.
Yeah.
This is my image.
so.
You gave it to me. And now I filter it. That's it.
Yeah, so I guess we just don't know that, like.
No, I don't know what is this image, of course, okay? Just as an explanation.
like it's the simple, like that's green, a certain green is the 7.
No, it's either if it's only one matrix, it's a grayscale representation. But if it's color, I have 3 of these, right? So I'm going to repeat this operation on each of the 3, the same thing. Just multiply numbers.
So in your camera, no outcome stays in
I-
follow to those numbers.
Yeah, but I'm interested in how this
It's
is.
like the idea of the sensor. This is what the sensor is doing.
You recall here we started with black is 0, 1 is white. Grayscale, do you understand? If are you asking about how a camera is working on what is the concept of representation?
I was wondering how, like, do we arrive at, I guess, like 7 is green? Like, how do we determine that 6 is yellow? Or, green, or like.
Oh, this is about the physics of cameras, which I'm not going to get into, okay? But if you just take some kind of a Photoshop or whatever, and you just put a number in the RGB in the right place, you will see that it's become yellow because of combination of 3 numbers. Okay, so this is artificially. How a lens and CCD is working, this is physics, which I'm not going to get. Okay, so this is filtering, and again, let me explain this again. So if I take a pixel and I'm using all its surrounding and basically averaging the surrounding with it, I'm blurring. Okay? If I sharpening is that multiply by 5 this pixel and put down all the rest is blurring. So it's sharpening. So I get a sharpening. Okay? Now people, there are many other filters, of course, and how people come up with them. Well, try and error. Okay, you can try to take these just to put other numbers, use it and see what happens. So edge detection is very simple because I now look for places that if I have black and white, that zeros becoming ones. This is an edge. If I would like to find edge here, first I'm going to put it into a black and white and then look for edges, for instance. By the way, again, I remind you that what we see and what computers see, it's not the same. We see here edges, right? Like they're in the rectangle, but there isn't. It's an illusion. Again, our mind faking a rectangle, but a computer will not see rectangle because there isn't a rectangle. Why I explain this again? Because there is something which is called SIFT, which is a very famous algorithm for image processing, which was used heavily before deep learning. And it finds out that there are specific features that numerically are maintained even if you are going to move around the object. Here we have some kind of a track, and you can see that those specific regions stays the same even if we are putting a track in some different angle. Now, why those specific regions? I cannot explain to you because it's not the way we see it. It's because of math. Okay? So this is something which people were using before in order to identify that the same object is in those two images. And it's a black box because it's something with playing with numbers. Foreground detection, meaning that I look at the image and I try to figure out what is the foreground. For instance, those people are the foreground. And here, I put them out. Okay, erase them. So this is only the background. An algorithm that identify what is the foreground and take it out. Okay, there are plenty other algorithms. Of course, I'm not going to go over them. The whole course could be only about this, but let's continue. After all those pre-processing, I can do useful tasks like detection. Detection is to detect objects, e.g., a vehicle on the road toll system. Of course, the road toll system needs to know that there is a vehicle that's arriving, right? Just to detect it. Recognition is basically object classification, meaning, okay, I detect that there is an object, but what it is? It's a car, it's a truck, it's a motorcycle. This is classification. Okay, recognition. Then there is the concept of identification. Specific person. Recognize a specific person face. This is identification. It's not only to detect that there is a face, but also to say this is Bill. Also, there is pose estimation. What is the position and orientation of an object? This is, again, very important for autonomous car, because if I see in front of me a car, is it coming ahead or is it driving away? Or it's a bicycle. What angle do I see it? Where is it heading? And motion estimation. What is the velocity of this object? I don't want to run over it. Okay? So those are examples for what I can do when I'm going to use more sophisticated algorithm on top of the previous ones. For instance, this is an example of object detection and recognition. So when it detects an object, you just put a rectangle on it. When it's recognized it also put the label. Okay, so this is the ball, this is the button, etc., etc. Note that it didn't detect and recognize the window, for instance. Okay, and
Table.
the table is, yes, it is. This is the table. Okay. Another example, pedestrian detection. Again, seat detection. Of course, it's not identification. I don't know this guy's name, but there is a person. Okay, it's very, very important for autonomous car. Let's see a small example of video object tracking. Okay, again, boxes around the people that it found, and then it put numbers on them in order to track them. Okay, this is, of course, very important for crowded places like airports. I would like to detect and, of course, to track people, maybe suspicious people. Okay, see that it works quite well here in the middle. Okay, but it doesn't work so well where it's crowded. Notice here that in the crowd, from time to time, it is confused and people are disappearing. It's not an easy task to track. Okay?
Give it a number, it's also sort of identification, because you like.
No, it's detection. It's detection, and just I put some number in order to track you and to know that you are still the same object, but I don't identify it. It's tracking number, it's not identification. Let's speak a bit about challenges in object recognition. Let's start with appearance. So let's start with illumination. One of the issues is illumination. I'm going to use again examples from the world of autonomous car. And in this light, and of course, this is twilight, so it's very difficult. And again, for us as human, it's quite easy to understand what is going on in this picture. Humans are excel in this, but for the computer, it's not so easy. Also here, see, it's a real issue. Changes in appearance. Most of us are not used to see bicycles at this angle, okay? And think of a computer that I'm going to give it examples of images of bicycle. If I'm not going to give it bicycles in this angle, it will not know to recognize that these are bicycles. Also, this is another odd way to look at bicycles. And here there is also bicycle from a total different view. For us humans, we identify immediately these are bicycles, but it doesn't look anything near this or that. Okay? Occlusion. Again, humans are great in see things that are not there. Okay? Here we identify quite easily that those are bicycles, but why? As a computer, I see here object 1 and I see there object 2. How can I tell that basically this is bicycle? Okay? And the same here. Humans identify bicycles here immediately. For a computer, why?
But don't we get this, how do you call this, hallucination of the network when they're making things up? Filling the gap.
If we are going to have enough examples, some of them also with occlusion, then the answer is yes. If we are not going to give for the learning step any image that also deal with this, maybe not, we don't know. Because it's not trivial to understand that those are bicycles. And complex background. This is one example. Keep in mind that the computer don't see, only numbers. The numbers here that we'll see will not make it easy for the computer to identify that there is an object in front of the wall. And here, did you see that there is another bike here? Okay, in this psychedelic colorful image. Those are real issues. And to end up, do you see the bicycle?
Yeah.
Now think about a computer that needs to identify this bike. We are not used to see bikes on ceilings, not at this angle, and also we have illumination issues. Questions? So this is what I'm going to say about image and vision. Of course, there are much more to say. We stop here. Okay, and now I'm going shift to why ANNs are great for image, but again, let's take 10 minutes break. Start again at 10 minutes after 5.
Great. אני כבר למה? יש לי 2. מה אני אומרת?
כן. איזה סרטון?
מה נשמע? שנייה. שי, אהלן. תגיד, שאלה. להרים את המאגר לקוחות שלנו על מפה בפאורפוינט, לפי הטובות. זה עניין של פשוט בשבילך. כמה שעות עבודה ואתה מבצע את זה? שהכתובת הנכונה, בסדר, אם שהיא לא נכונה, פשוט לא תציב, ונגיד אנחנו צריכים לתקן.
איך הסכומים האלה?
יהיו כנראה אחוז ניכר שהוא לא יהיה בסדר. מאוד לא כמה אלפים שזה לא יהיה בסדר, אבל יהיו כמה אלפים שזה כן יהיה בסדר. אז בואו ננסה לעשות הצגה. תוסף קומפאונד, אני אשלח לכם מסודר מחר בבוקר. תוסף קומפאונד, תכתוב שם כמה פרמטרים, כאילו לחפש, אתה יכול לחפש, נכון, לפי ריג'ן, לפי סיילס פרסון, כאילו, אתה מדליק פקטורים ומשליח בצורה, נכון? זה פשוט.
תחום מסוים של המנוע. התחילו לייצר מהם שנתיים, זה לא דומה, זה חרן פעמים.
אתם מבינים את הטוב הזה. אוקיי, זהו, אז זה תסתכל אם תגיד לי. בסדר, זה נקודה חשובה. כי אם אפשר להרים משהו כזה בכמה שעות עבודה, יש לכתוב, אפשר להרים משהו במשת עבודה, ואני יכול להגיד להם, אוקיי חבר'ה, זה טוב לכם, אז סבבה, אז בבית קדם, כאילו הסיילספורס, דיברנו על הסרט, אני מבין שהם מדברים על פיתוח וזה, ואז כל שינוי זה התאמה, וכל נושא של שדה זה התאמה, אצלך אני רק מוסיף שדה לטבלה וזהו, נגמר הסיפור הרי. זה נורא פשוט כל דבר כזה צריך להיות, בואי ושעובדים פאור כן, אבל אני רוצה לחבר את זה אחר כך, א' לא פאור זה יותר יפה, ואני רוצה לחבר את זה לסיילספורס. אז בסיילספורס ובפיתוח, ועכשיו צריך להוסיף שדה, זה לגלגל אותו למעלה, אבל להוסיף אותו בפיתוח לזה, אבל הכל נורמלי, כל דבר זה כל דבר קטן זה יישום, ועוד שעתיים הוא כמו שעשית את הכל שלו. טוב, בסדר.
תקשיב, יש לי רחמניות, יש לי תמרים, יש קדים. וואו, אנסטסיה, מה זה? אני היום באתי עם ציידנית. יונה. היי תמר. ולהתקצר על השם. יש לי כדורים. זה נמשיך. יש לי גם כאלה. עד 8, אני אוכל.
כולם מסתכל.
לא, בגלל זה לא יכול להיות, אני הבעיה.
Machine learning, by the way, deep learning is part of machine learning. We may find in several articles people are speaking on machine learning or deep learning. Well, those people don't understand what they are speaking about. Deep learning is part of machine learning, but machine learning older approaches were not using the methodology of deep learning. And what they need, they require first defining attributes or features from the images, extracting features from the images. Deep learning techniques are able to detect objects without defining those features. What does this mean? This is slide that you're familiar with, but this is a different one. This try to compare deep learning for images and other machine learning methods. So let's start here. In other features, ignore, we're not speaking about the label, okay? We took the pictures and we need to extract for them images, features like shapes or contours or edges, whatever, before we did the supervised learning. And then if you wanted to use the model, again, you need to take the image, extract the feature, and do this. Until about 10 years, this was the way that people were doing this. And this means that we as humans try to extract features, but what is the problem? That machines don't see images as we humans see them. So we think that shapes or corners are important, but they are not. Okay? Nowadays, when we use deep learning, we just give to the network the numbers of the image. That's it. We don't try to extract anything, sorry, and it works. Why? Because those networks nowadays are called, there are specific type of deep learning networks that are called CNN. DNN is deep neural networks. CNN is called convolutional neural networks. It's a class of deep neural networks. And they use something which is called convolution for at least one of their layer. What is convolution? Is a very fancy word for averaging. Okay? And it's the same thing, exactly the same concept that I told you before. Using those filters, okay? This is convolution, and the same slide that I showed you before, okay? Why it is averaging? Because I multiply 9 numbers and divide by 9, right? So this is averaging. So the current architectures of those networks look something like this. I'm taking an input, and again, of course, I don't take this, I take the numbers that the computer see. I'm using some type of convolution, and this is layer, this first layer, hidden layer. Then I'm doing something which is called subsampling, which I'm going to explain in a minute. Why? Because, as I told you, in images, there are plenty of numbers because it depends on the resolution. Let's say it's 100 by 100, so it's 10,000 dimensions. It's a lot, okay? So this is why people are using subsampling in order to shrink it. Otherwise, so many numbers, it will take ages. And then again, they are doing some kind of convolution and trying to subsample again and to get an output. Why does it work? Well, it works. Again, why? Because, so what is subsampling? It's very easy. I have a big matrix, 4 by 4, and I would like to create from it 2 by 2. So one of the way to do it is what is called max pooling. What is max pooling? I split it to 2 by 2, And I say, okay, let's look at the numbers. Which one is the maximum one? 6. Well, let's take it. That's it. So I just,
Don't we missing like, yeah, we're missing like all the rest of the information, where
we are,
the vast majority of it.
but it works. Don't try to think why it works. People, okay, of course, when people are going to publish their paper, they are going to explain in very clear words why it is the wonderful the dawn. But actually what happens, they tried many, one of them worked, so this one is now published. That's the reality, okay? So it's working. Now there are other ways to do, because again, I cannot take the maximum number, I can average. I can do several tricks in order to represent those 4 numbers with one number. So maximum is one trick. I can try several of them. The one that is working, I'm going to publish. Sorry. Now the electricity doesn't work. Amazing. So why deep learning is so great for vision? Because when I need to do a manipulation on a picture, all information that I require in order to do it is in there. Because everything in the image is numbers. All numbers are there. Okay? And those numbers are the pixels. And if you recall, when I told you about what are manipulation or images, is that multiply them by other numbers, by filters. So we are back to numbers. This is exactly what neural networks excel in. Okay? If I have some other issue, not vision, let's say I would like now to identify suspects. Is it going to be enough to take the picture of them and to classify which one is a suspect, which not? Of course not, because the information is not only in the image. I need to plenty of other information, which I don't know what. So here, I don't need it, because if I'm going to do something with images, all information is in the image. So it's going to be very easy for me. This is why it's Excel, and also because images are numbers. And it happens to be that any topic that people find out a best way to represent whatever they need to do in numbers, deep learning is starting to work. For instance, text, right? I'm going to explain about text. I'm going to get back to this point. If I don't have a very good way to represent my features as numbers, neural networks or deep learning is not going to work for me. Okay, and this is why I told you before, it's in hype. It's doing great job in images and in other fields, but not in all of them. It's not going to solve all our problems, and it doesn't do coffee.
Not yet.
Not yet, at least not.
Can you give an example of something you cannot represent?
Yes, for instance, I would like to open now a matching office to match couples. Can you put it in numbers? Do you have an idea how to do it? I don't. At least not yet. Maybe sometime people will find a way. Currently, I don't know. And other, of course, other application in real world, not everything can put in numbers. Basically it can, because I can represent them in the computer in numbers, but not necessarily in a useful way. For instance, of course, I can represent text as numbers because I have Word document, right? But until people find a way to embed something which I'm going to explain later in the course, text as very, very long vectors of numbers, it didn't work well. Okay, so it's not enough just to find
some way to digitize it. You need to find a way that the numbers make sense. And in images, they are making a lot of sense because basically this is all the information.
But basically what is missing is sensor that will be able to convert the reality into numbers.
Again, sorry?
I'm asking if what I from the example that you mentioned, what I think is missing is a sensor, like in the camera, we have a good sensor that can easily
But it's not only sensing.
convert the view into
This is
a string of numbers.
this is one part.
For emotion, for example, we do not have such sensor, and therefore we cannot deal with emotion in deep learning.
Yes,
Not
but
because deep learning is not good
it's-
for emotion.
It's more than that, because it's not just how to sense it, it's also how to represent it. Okay, if you know to solve those two, yes. Now, basically, since all of us are cells and all cells have ingredients, and ingredients you can measure them, basically you can take everything that is in a computer and represent it as a number, theoretically. If people will find a way to do it, it will work. Probably. Okay? Till now, nobody knows how to do it, as far as I know. Now, a major drawback in deep learning, it requires a lot. I mean, a lot of training data and a lot of computer power and a lot of images, okay? And nowadays, as I told you before, we have this specifically for images. This is, again, why deep learning is really, really great for images. And this is a real revolution in many applications that we need to use for images. For this, deep learning is here to stay, and it's doing great. As I told you, it's not going to solve all of our problems, but at least this field actually was solved by deep learning.
When you say images, you mean both photo and videos, right?
It's the same. Some application that you can find on the web, for instance, you can take pictures of older people, and deep learning is going to generate, using what is called AI generative, which I'm going to speak about later, images of them, how they looked where they were children. In other way, there is a very nice website. You can upload whatever image that you would like to see, and it's going to take out the foreground, the background, okay? You're going to left only with the foreground. Very nice website. Another thing that people are using deep learning is for brand monitoring, because each company wants to know whether their brand appears in some picture, in Facebook, Instagram, TikTok, whatever. So people are using this monitoring, and whenever it appears, of course, the company wants to know what is the context. Is it good context, bad context? Okay. Of course.
Even if it's we see here that it's not being related correctly, the brands.
It's just an image I found freely on the internet.
But is it also able to identify the misuse, the fake image? Because here it's the misuse, it's not the original one.
It's just an image I found on the internet. Don't put too much attention for this. Of course, if it's, as I told you, face recognition now is done. In the past, face recognition was using some kind of a network to measure the distances between eyes, nose, etc., etc. Those were the features that were extracted in order to learn to represent people. Nowadays, we don't do it anymore. Just give the computer the faces, and like magic, face recognition works very fine, very good. Very well, sorry. Okay, and of course for surveillance, if you know, in many countries, China, UK, we have a lot of Israel, we have a lot of those camera, and there is deep learning algorithm that know to identify people and to identify behaviors, etc., and it's going to be better and better as time will flow.
There's some technology that's like a special print people can wear And then the recognition cannot catch it because it's like making it like,
To fool the algorithm? you mean?
Yeah.
Yes, we are going, this is called adversarial AI, and I'm going to cover this at the last class, okay? There are, of course, military applications, satellite imagery processing, it's very important for military applications, detection of soldiers or vehicles from images or video, either by a drone or by a satellite. These are applications that we already have and they are working. Missile guidance, of course, at the missile head. Nowadays, you can have image processing algorithm that know how to guide the missile to the right point where to we arrive to the area by GPS, but at the end, the last mile, it will know by guidance of image processing to do whatever it needs. Autonomous vehicles, we have more and more, and I'm going to dedicate a class to discuss the future of battlefield. And of course, this is one important field in it. And of course, the autonomous cars, autonomous vehicles. In order to get machine sensing and perception, you must have those deep learning algorithms in order to understand your whereabouts and what is going on, etc., etc. Of course, you need to identify the images, you need to identify traffic signals, and of course, those. And it's not enough because you don't, for autonomous car, you don't need only to have the sensing, as I told you before. You need also to know to represent your knowledge. So it's either about localization, also about tracking and prediction of the images that you just noticed, where they are going to be in next minute, what is their velocity, and how to represent it in a clever way in order to use it. This is not enough. You also need a way to plan ahead, and you need to control the vehicle, of course. And for this, you need machine learning, deep learning included, and you need automated reasoning and problem solving, and more things that I'm going to explain later in this course. If you believe that autonomous cars are going to drive soon, well, you may be disappointed because it is going at
Saying that the upside of the
Yes.
2 years ago and the downside of
it
the
is going to take, I don't know how long, but let's say 20 years, maybe.
Because it's
Yeah.
not.
Oh, yes. Okay, so again, a hype, but there are so many issues with this. So it will take time, but is it going to succeed? Yes, but it's premature nowadays. Okay. Just give you one example. Why? This is an example that I'm using. For those of you from abroad, I'm going to reveal a great secret about Israel. Israeli drivers are not the greatest drivers in the world. So now think about a winter day. You are getting to a traffic lights. It's not working, just blinking with yellow. And now everybody wants to cross. And the autonomous car is going to get there. We'll find it 2 weeks there afterwards, still in the same place. Just consider the car trying to cross the junction when Israeli drivers are around it. It's not going to work. Okay, this is what one illustration, but there are many other issues with this.
But if everything will go into autonomous car, like we say, there is no enter for humans to drive to the city, only for autonomous car.
There is a saying that if my grandparents has wheels, he was a bus. No?
Yeah.
If I'm speaking about reality, not
I know
about
this
fantasy.
story about the grandmother, grandfather, but
Questions? So I plan to start a new topic, but I'm not going to do it. But sometimes I will have to do it. As I told you, there are only 12 classes. If there are no other questions, see you next week. Right.
We have burning.
פה בליד.
מה זה את כבר? סבבה.
מה?
תומר?